Hello, hello, Surya, do you hear me? Hello, 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 do you hear me? Hello, we'll wait 1 or 2 minutes to get somebody on online. Hello, Manjudan, do you hear me? Manjunadan, do you hear me? Hello, do you hear me? Do you hear me?
Yes, sir. Yes, sir. I'm able to hear your voice.
Okay, just a few minutes we will wait and then we will start. I'm
Okay,
waiting
sir.
for at least 1 or 2 more to join.
Okay, sir.
Okay, now at least two of you are there. We will see. Do you see the screen?
Yes, sir.
Okay. We will wait for a few minutes more. Who has joined? Anybody has joined?
Yes, sir. Surya Kumar from
Surya
IIT.
Kumar,
Yes, sir.
IIT. We will wait another person, somebody from Cochin.
Okay, sir. Hari Prasad.
Hariprasad, have you joined?
No, sir. No, sir. Not yet.
Not yet. You are waiting. Manjunath, what is happening in your institute? Anything very great things happening?
Not like this, sir.
Huh?
Routine work is going on. Routine thing is going on.
I didn't follow. Any great things are happening?
No, sir. Routine things is going on, sir. No special.
I see.
So how are you, sir?
I'm okay.
I think after 1.5 months we are in hangout again, sir.
Yeah. At least this keeps you to learn something. Correct or not?
Yes, sir. Yes, sir.
Otherwise, you will be spending your time
Yeah,
in
that's
other
true, sir.
activities.
In other activities.
Whether useful or not, I do not know. But still,
It's useful, sir.
I'm just waiting for somebody from Cochin to join so that we can start. I don't think many people are interested in this topic. What is your reaction of your group or your center on CO2 presentation of ours? Are they aware of it?
Yes, sir. They are aware of it. They asked me which one
Huh?
is. They are aware of it, sir. And they
Uh,
asked me which product is good, which product is more important from CO2, like that. They asked me. So I told like dimethyl carbonate and methanol will be more important from carbon dioxide to carbon dioxide transformation, like that. I told. So they told okay, like that.
I see. But we didn't deal with what is important. We deal with what has to be done. Am I right?
Yes, sir. Yes, sir.
If you know what has to be done, then automatically you will do what is important.
Yes, sir.
You can send an email to Hariprasad. Do you
Okay,
have
sir.
an email?
Yes, sir. I have. I'll send him, sir.
Uh,
Okay, sir. I sent him, sir.
okay, well, we'll wait few minutes so that he will see the mail and then
Okay, sir.
because he has not joined till. I heard that there is some important meeting in your center to next week or 18th or 19th.
18th or 19th? No, no idea, sir.
No idea.
But no idea.
I thought you are also involved.
It's not. I think in next month there is a function, sir. I don't know about the meeting. I
Uh,
think RSC meeting is there, sir. Yeah.
uh,
I think RSC meeting for faculties is there. I think so. Next week. But I'm not much aware of it.
huh?
I'm not much aware of it.
Hmm. I thought you are all you research scholars are going to be evaluated.
No, sir.
It is not
No,
so.
sir. No, sir. No. External evaluator will be coming. External person will be coming. Last year, Krishnamurti sir having came here.
Yeah. This time also he is going to come,
Okay,
but
sir.
some more people are going to come from Indian Science.
Okay, sir.
So who is completing PhD in your group now? Anybody?
Yes, sir. In this, I think November or December, 9 students will be completing the PhD.
9.
Yeah, 9 students.
Fantastic.
5 from material science,
Uh,
and 2 from biology, and 2 from theoretical physics.
uh, very great.
Yes, sir.
All of them are registered with Bangalore University. Yeah?
No, sir. It's affiliated with Manipal University.
Manipal.
Yes,
Okay.
sir. It's like Mr. Vijay Kumar, Mr. Janardhan, and Mrs. Shweta. All
Uh,
these people will be completing their PhD.
I see.
Yeah.
Do I know them? Any one of them?
What, sir?
Do I know any one of them?
Yes, sir. Yes, sir. All the three. You know about all the three people, sir. Because all of my three seniors have attended this NCC program also.
I see.
I think you remember them, sir.
I remember one of them.
No, this time to Nagpur also, they came, no, sir. You also
Yeah, yeah.
spoken with them.
I may remember by face, not by name.
Okay, sir.
Because in a year, so many names are. I have to put it in my mind.
Thank God you remember my name, sir.
Those of you who are. What do you mean? It all depends upon how you interact. No.
Yes, sir. That's true.
See, memory means it has a finite number. So unless otherwise there is an interaction back and forth, that the memory will not retain it.
Yes, sir.
So it has to be back and forth. Only forth is no use. We wanted to do something with you people, but nothing coming out.
No, sir. It came, sir. Actually, sir had involved me also.
Uh,
So I'm also doing some literature survey.
uh,
So, sir told that last week there was a meeting with you through Skype
yeah,
like
but
that.
it
He was
did not
telling. But
happen.
due to some internal problem, it was there was a problem here also with internal problem. So he
Uh,
could not able to join in with you in the internet.
uh,
But I don't know about the current thing. What is going on, sir? Current thing.
mm. Yeah, yeah, we also had that problem. Last week we had terrible problem.
Okay, sir.
I was so unhappy that we could not start it on the day.
But everywhere there was internet problem, sir. Here also there was an internet problem.
Mm.
There were also some internet problem. Okay, ನಾನು ಕಳಿಸ್ತೀನಿ ಸುಹಾಸ್ ಅವ್ರನ್ನ ಕಳಿಸ್ತೀನಿ ಎಕ್ಸ್ಕ್ಯೂಸ್ ಮಿ ಸರ್ ಐ ಬಿ ಜಾಯ್ನಿಂಗ್ ಇನ್ 2 minutes a few minutes.
Okay, okay.
Okay, sir.
We are coming soon. Surya, you please wait. We are just waiting for one or two people to join. Do you hear us, Surya? Manjunath, are you back?
Yes, sir. Yes, sir.
You are back.
Yes, sir.
Hello.
Yes, sir. I'm back, sir.
Okay. Probably we'll start because we will not wait for anymore. So, good evening to all of you. As you all are aware that we have been having nearly a month and a half vacation. I hope you are all re-energized to look at the energy problems again. Now I must tell you something about why this course and why this course at this time. These are the two things I must emphasize this, because many times we assume that it is all known, but many things are not known or not explicitly stated. For example, one of the examples I will tell you, which you can easily recognize, why hydrogen is the best fuel. We are only talking about hydrogen oxygen fuel cell. Why hydrogen is the best fuel? That type of questions we don't ask. This is one thing. Second type of question that we are going to pose is why electrochemical energy systems are in a way different from the energy conversion devices that we are used to. Okay, I must tell you here. Okay, with this you might not have read anywhere, but I must tell you the energy density from an electrochemical energy system is far superior to the energy density of any other energy conversion processes. I will explain this to you, then only you will understand. For example, you take 1 liter of petrol. Okay, it has certain amount of energy. Let us assume energy is measured in terms of some kind of a heat quantity or free energy quantity, doesn't matter. Now if you take an electrochemical system, I will take an example of the electrochemical supercapacitors. Okay, so now if I were to take a volume or weight basis, whichever way you want to look at it, because petrol is all, or diesel or fossil fuels are always measured in terms of the volume, because of the volume is more important than the weight because density is low. Therefore, if you take on the basis of volume quantities, the electrochemical supercapacitors will be at least 10 to 100 times more energy density materials than compared to the all other known energy systems, whether it is fossil fuels, whether it is anything else. Okay, we will not go into details of them today. So that is why there is an yet another advantage with the electrochemical energy systems. I'm sure you would have heard about it, that it is the available green process. Okay, so therefore it doesn't give rise to any of the greenhouse gases or any of the harmful products. Okay, harmful means it is not only harmful for human beings, harmful to the surroundings. Okay, to the environment. That is what we are worried about. In the electrochemical system, the conversions of the conversion products are easily acceptable by this environment, and the heat that is generated also is a dissipative heat, not a concentrated heat. Whereas if you take for example, you are going to burn petrol, it is not a dissipated heat, it is a concentrated heat. It will heat up the carburetor or something like that. You run a car and then after 100 kilometers or something like that, you open the bonnet, you cannot touch that bonnet. Only fumes will be coming or water vapor will be coming. So therefore, there are various reasons why electrochemical energy systems are necessarily has to be better than the all other energy conversion systems. We will, as we go along, we will talk about it many more times, many more aspects. I have only given you two aspects today why electrochemical energy system is important, because on the volume basis or on weight basis, in whatever basis you are going to do calculate, the net energy density that you can derive from an electrochemical system is going to be an order of magnitude higher than the other electrochemical energy systems. That is one thing. Second thing is all electrochemical energy systems are environmentally acceptable. I am not saying environmentally safe, but environmentally acceptable. Now, the point that we are going to talk in this presentation, chemical energy to electrochemical energy. Okay, So energy can be stored in any various forms. One of the forms is the chemical energy. That is how we are storing the energy. So chemical energy conversion to electrical energy is known to us for a number of years. As a matter of fact, it is known to us ever since the water electrolysis was postulated and carried out as efficiently as possible. Okay, it is not most efficient, but as efficiently as possible. So the conversion of the chemical water electrolysis is a electrochemical energy conversion process, because you are producing a fuel, hydrogen. So therefore energy conversion, chemical energy to electrical energy, is known to us for maybe more than 2 centuries. Even then, the first postulate, we are going to see the history of the fuel cells. In spite of it, nearly 170 years of research has gone in, but these devices have not become commercial. This question we have to answer, and this question we have to answer from the point of view of when it is going to be commercially viable. We cannot be going on saying it will be commercially viable. It will be commercially viable sometime or other, that is definite, but when, we must know this. Now, the other aspect of the energy conversion processes in the electrochemical sense is that it is the most simplest device that is possible. Only there are two components, two electrodes which are solids, and one electrolyte. Electrolyte can also be a solid, can be a solution, or can be anything else. Okay, we are not worried about it. So there are only two components, two electrodes and one electrolyte. Okay, both the electrodes are solids. So when we have such a very simple two component system, we know very well in the phase diagram the two component system is a well understood system. That what do we mean by two component system is, we are understanding all the possible changes that can happen in the two component system. So in the phase rule, we have understood the two component system thoroughly, but the same, when we make this two component system into a device, we are unable to do that. Why has happened? Okay, this must be very clearly understood, because this is a just like a phase rule diagram. Phase rule diagram is solid, liquid, gas. That is all the phase rule deals with. When a substance will be a solid, when a substance will be a liquid, when a substance will be a vapor state or a gaseous state. So therefore, this equilibrium only is what we are looking. Here also we are looking that only. We are taking only the interface and putting a gas and producing a liquid, water. Put a hydrogen there, produce water. So therefore, from the thermodynamic point of view, we seem to be understanding this two component system of the fuel cells, but we are not able to make a device out of this. Whereas we see, you take your water, you know how to make a steam. You take water, you know how to make ice, but you do not know how to make the energy out of the hydrogen. That is what is the problem here. So why this frustration has happened? We saw nearly 2 centuries have passed. We have not been able to succeed in this. So this presentation is going to be specifically focused what has gone wrong, or if nothing has gone wrong, why this delay has happened. If people think that there is no nothing has gone wrong, then the delay has to be answered, because human mind is such a perpetual machine. If it wants to do something, it should have done in 170 years. What has gone wrong, or what is it that we have not achieved in this, has to be uh, answered in these presentations. So in all these aspects, this presentation is going to be a totally different presentation compared to what you would have been hearing about fuel cells. We are not saying that everything is going to be new, but we are going to approach the fuel cells from a new perspective. That is what is. We may be looking at few of the options that has been already done. As I told you, unless otherwise I know what has been done and what has gone wrong or what has gone not correct in the past, that has to be rectified or it has to be changed. That is what we are going to see. So I have already talked to you about the unique position of the electrochemical energy systems. I am not going to repeat it again and again, but not only from the greenhouse that it is a very environmentally acceptable. That is not the reason. There are various other reasons. Okay, so this is why I put some known but not explicitly stated. Electrochemical energy systems is one system where the conversion efficiencies are going to be really above the Carnot efficiency. We have always understood that the efficiency of an engine is going to be governed by the Carnot theorem. But here electrochemical systems are not going to be only restricted by the Carnot theorem. So therefore it has a unique position. Later on we are going to show it to you. You will be surprised if I tell you an electrochemical energy system can give me 110% efficiency. It can be even greater than 100. The reason being the efficiency is in terms of the delta H and delta F. So depending upon the delta S term, delta H can be greater than delta F or delta H can be less than delta F. So therefore the ratio can be greater than 1 or less than 1. So this is the unique position electrochemical energy systems has. We are going to look at these aspects more clearly little later, but I'm just telling you that this is one device where you can have more than 100% efficiency. Then I have the next point I have already told, therefore I will not repeat it, that it is the environmentally acceptable device. All other energy conversion devices are in some form or other, okay, may not be totally unacceptable, but it may be partially acceptable. But the electrochemical systems are totally acceptable from the point of view of environmental thing. Third one is the specificity. For example, if you are taking a fossil fuel and combusting it, you have no control over the product that is formed. Ultimately what you want is CO2, but you will be forming simultaneously CO, you will form some partial oxidation products, all other things can happen. Whereas here, because of the potential, we will see what is this potential little later, because that is a very important parameter we should understand. Anyway, we will look at it from the point of view of understanding. Okay, because of the applied potential, a particular electrochemical reaction alone is possible. So therefore what happens here is, if I want to combust a fuel only in the partial mode, or if I want to combust it only in the complete combustion mode, I can do them exclusively. Whereas that is not possible in the thermal energy conversion devices. Then we have to look at it from the point of view of electrical energy versus heat energy. I must tell you what this means. Okay, this is a very obvious statement I have put, but there is a tremendous amount of information that is required. What we are talking about is, we are talking about electrons versus chemicals. You will immediately say chemicals also is consisting of electrons. Yes, chemicals also consist of electrons, but what we are talking about it, chemicals consist of electrons and others, whereas electrons are only. So electrical energy is electrons, whereas heat energy is the chemicals. So therefore you can see that when you are converting a multiple component system, there has to be loss. That is why all devices where the heat is the source of energy, the efficiency is less. Whereas in electrical energy, I just now told you, the efficiency can be even greater than 100%. Maybe subsequent lectures I will show you to you mathematically how it is going to happen. But anyway, so now what is the question? Because we must proceed now. The question is, are we going to look at it as electrons versus chemicals? So if it is were to be the question of electrons versus chemicals, electrons are better energy conversion devices than the chemicals, because electrons are single entities, single processes, whereas chemicals means multiple species, multiple things, multiple processes. So this is so obvious for us. These are all nothing new about it, but we have never realized it. Then as I already told you, that the system components is very simple. Okay, the system component is only two component system. one electrolyte and two electrodes. That is all. Two component system. So as a component of a device, fuel cell is the simplest device that is possible. Just like you, for example, you have a matchstick and a place to rub it. So it is a two component system. You can light the fire. The same way here. So, but what is the problem? Is the question. The possibility of adding complication is the multiphasic system. Okay, if the two components were to be only giving rise to a two-phasic system, then it is, for example, you take a matchstick and a place to rub it, so therefore it is a two-component system. Two solids are interacting with each other. But here that is not true. Even though there are so many only interfaces, but the interface is not a well-defined parameter in this, because a solid, a gas, a liquid, many other things, okay, not even a liquid, it is a solution, okay, there are varieties of ions are present. So therefore the system components is simple, but the system behavior is so complicated. We have to understand them. So that is another thing that we have to, that is one of the reasons why that accounts for this 170 years of research. We have not yet succeeded. We will come to it all these issues as we go along. Then there are variety of choices. We are going to show you to you what are the choices that are possible, at least some of them. Okay, anything can be used as a fuel. Okay, but even sand can be used as a fuel because silicon can be oxidized. But wide variety of choices are available, but only few of them are exploitable. Okay, this is the reason why, for example, why are we thinking of only hydrogen oxygen fuel cell? Why are we not thinking of any other fuel cell? This is a problem. The problem here is we want to keep the interfaces as simple as possible, and the simplest chemical that I can deal with is one proton, one electron. That is the hydrogen. Okay, I hope I already have talked to you electron versus chemicals. So the moment I am going to have other chemicals, I am going to have more protons, more neutrons, many other things are going to happen. Therefore the combustion efficiency has to come down. Okay, I hope you understand this. So therefore one of the answers why hydrogen in the fuel cell is that it is the simplest system other than the electrons. Okay, it is only an electron and a proton, electron and a positive charge. That is all. Whereas if you take any other chemical can be used, but they cannot be exploited so easily. Then the final point, some known facts but not explicitly stated, is fuel cells are controllable. Just now I told you, controllable means it all depends upon what is the potential. What is the potential means, I want to throw a human being, I can throw him from the 11th floor, I can throw him from the first floor. So all that I have done is the potential is changed. So the the possibility of him surviving is more when he is in the first floor than when he is in the 11th floor. So when the potential is changing, the process is controllable. Okay, I can still throw him out but keep him alive. I can throw him out and make him die. So therefore this process is controllable. Okay, and then there is yet another possibility is when we combust, we cannot divert the process. I hope you understand. For example, I want to combust a fuel to a particular product, I can divert it in that direction, even though many other combustion products are possible in the thermal combustion, but it is not possible. It is possible in the electrochemical system. Only one of the products can be selectively obtained. So I want to, for example, I want a partial oxidation, I can do. I want a complete combustion, I can do. So therefore what it means is the flexibility, the diversion, the controllability, and the amenable for scale up are all possible in the fuel cells. Whereas sometimes in the conventional energy devices, they may be possible in all these things, but they may not be amenable for scale up. So variety of possible situations are possible. So now quickly looking at Next is what we are doing is I'm taking the chemical energy and going ultimately to the electrical energy. I hope that you are able to see that is the starting point is chemical energy and the ending point is the electrical energy. How we go that is I take the chemical energy, combust it or heat it, thermal energy, put the thermal energy into the internal combustion engine, make a piston move. By the movement of the piston, you produce the electricity. So therefore, you can see that I have to take a route, a long route. Uh, Here I have only shown 3 of them. There can be multiple steps here, but we will not worry about it. So therefore, even if I were to carry out this process, chemical energy to thermal energy is 80% efficient. Now thermal energy to mechanical energy, just a minute, just a minute. Hello? Yes, sir. Okay, thank you, sir. Yeah, I will do that. Don't worry. Thank you, sir. Thank you. Thank you very much. Thank you, sir. Yeah, everything I heard, got. I have read everything. I have a hard copy myself. Don't worry. Thank you, sir. Thank you, sir. So even if the chemical energy were to be converted to thermal energy at 80% conversion, and thermal energy into mechanical energy as 80% conversion, then chemical energy to mechanical energy becomes a 0.8 into 0.8 to or becomes 64, 0.64 only. So therefore, when we go in the multiple routes, you can see that the efficiency goes on decreasing. Whereas if you take chemical energy, directly put it into the in a fuel cell and convert it into electrical energy, then the efficiency is whatever you are getting. So this is the second advantage. That is why I hope you are understanding now. This is simply chemical energy to electrical energy is harnessing the electrons. Here we are not only harnessing the electrons, in the multiple path we are harnessing it various other processes. That is why we put in the initial stage, are we looking at only electrons or are we looking at the fuels? So now quickly looking at it, you can see here on the right hand side, I hope you are able to see, I have given the energy density. Okay, this is what I was talking to you in the beginning. Energy density is given as watt-hour per liter. This is volumetric energy density. I have already told you why we are talking about volumetric energy density and not the gravimetric energy density. There are various reasons. We have already talked about it. We will see later on also when we are going to look at a few of the new concepts about supercapacitors, batteries, and all those things. Okay, but I hope you are able to see where we are standing. Okay, at the moment, even if I want to compare the energy density of the electrical devices only, okay, not even the thermal energies or the fossil fuel energy, therefore nickel cadmium battery, lead acid battery, I hope you are able to see all of them here. Then you see methanol air battery, but you see where the fuel cells are. Fuel cells are higher. Even above that will be the uh, supercapacitors, which we are going to see at the end of this presentation. Not today, at the end of this presentation on this series. As we went last time, I must warn you that you are in for a trouble for another 30 lectures in this, or more or less, I do not know. So but what is the problem here? Okay, if this is already possible, why are we not exploiting these energy conversion devices, these batteries or storage devices? Okay, the problem here is many of these storage devices, batteries, are needs recharging. This is a problem. So therefore there must be active period and inactive period. That is not possible for an energy conversion device. Energy conversion device must be capable of giving energy whenever I want. I cannot wait for it to recharge. Second thing is, I hope you are already seen lead acid battery, nickel cadmium battery. All of them are some kind of a hazardous chemicals. I will not talk about them today or even in the presentations that is going to come, but they have their own limitations. We will leave it at that stage. Now, so So therefore, these solid state devices or solid liquid devices like this, the batteries, or solid electrolyte devices like the batteries or supercapacitors, all of them have some limitations. Now, internal combustion engines, Carnot limitation is already known. Second thing is it goes through a mechanical energy conversion. Therefore, there is a moving part, and therefore, necessarily there has to be loss by the friction. So, when there is a moving part, it has to produce sound. So, noise pollution is going to happen. There are various other things. We will not go into all of them. So, from the point of view of fuel cells, their efficiency is higher than any of the energy conversion devices. I have already talked about it. We are going to show more mathematically the efficiency. The reliability of the fuel cell can be increased tremendously in relation to thermal processes. For example, in the morning you will have a problem with the combustion of your fuel. You will put a choke or whatever it is. That is another. Cleanness, I have already talked to you that it is green process. Now, as I told you, unique operating characteristics. You apply a particular potential, that is enough. Whereas that is not possible with the combustion process. You have to increase the fuel sometimes, you have to decrease the fuel, you have to go on altering things. That is not necessary here. Okay, as I talked to you, is a planning flexibility is there. You can plan whether you want only a single combustion product, a multiple combustion product, whatever it is. Okay, in addition to that, there is a tremendous amount of development potential. We will never be able to reach the final point. Today we can say this fuel cell is good, tomorrow something else can happen, some other fuel cell will be better. So therefore, since the number of choices available to are higher, the development potential is tremendously enormous. Now, quickly looking at it, this is a very simple picture. Quickly looking at it, the fuel cells are normally considered in three different ways. One is what is the electrolyte, that is what is done in the left hand side. Okay, it can be alkaline fuel cell or phosphoric acid fuel cell or molten carbon fuel cell or solid oxide fuel cell. Or you can, on the right hand side, I have shown it to you the temperature of operation. Okay, low temperature operation, low temperature fuel cells, PEMFC and direct methanol fuel cell, medium temperature fuel cells, phosphoric acid and things, high temperature fuel cells, molten carbonate and solid oxide fuel cells. These are the another way of classifying them. Yet another third way of classifying them is the species that is transported from between the electrodes. It can be protons, it can be hydroxyl ions, or it can be carbonate ions, or it can be oxide ions. So you see, this is the problem that is existing. When we talk about the fuel cell, when we want to compare, we are having all the operating parameters different. The electrolytes is different, temperature is different, the species that is transported is different. Therefore, we cannot talk about an efficiency of a fuel cell in relation to another fuel cell, even though we are talking. I hope you understand this. We cannot talk about them in the same way. For example, even though for example, you take the proton exchange membrane fuel cell and direct methanol fuel cell, the transporting medium is the same, protons, the temperature is more or less same, but still they are not comparable. Okay, that is because methanol has to be put only in the anode. If the methanol is going to cross over, I hope you are seeing the picture here. If you look at the picture that is given here at the bottom, it is not there, but you can imagine that is the methanol. It can be transported from the anode to the cathode. Therefore, the cathode reaction will be undergoing some problem. Okay, so we'll come to it. That is what is called methanol crossover. We'll come to it later on. So therefore, this is the problem that is existing. So therefore, we will not worry about all these things. But what I have tried to show here is that the development possibility, that is what I told you last time, last point in the last slide, is that is what is here. There are varieties of this. Not only this type, there are many more possibilities. I can have a biochemical fuel cell, I can have a variety of them. Okay, air breathing fuel cell, air non breathing fuel cells, variety of them will be possible. You will see later on. Okay, so now Okay, forget about all those things. Now let us look at the fuels. What are the fuels that are possible? Hydrogen, methanol, ammonia, hydrogen, formaldehyde, carbon monoxide, formic acid, methane, propane, whatever may be. Okay, okay. We have only listed few of them here because of space. So energy density is what is more important. The last column is important. All other things are known parameters. Okay, all of them has to be around 1.2 volts or 1.3 volts. That is the maximum that is possible here. We will come to it later because it is an electrolyte medium, so we cannot do anything beyond that. So, but you can see the best energy density, even in terms of the gravimetric energy density, if you take, because it is a gas, that is why we are talking about the gravimetric energy density. So you can see the next best fuel is methanol, which is 5 times lower than the hydrogen. I hope you are able to see 32 units and 6 units. So any other fuel that you think of will be only be less than the energy density of the hydrogen. So this is one reason why hydrogen is used. I have already talked to you why hydrogen is used. Okay, one electron, one proton. Okay, that is another reason, because when you are harnessing electron, your efficiency goes up. When you are harnessing electron and other species, your efficiency goes down. There are many other reasons. We don't have time now to talk about it. We will see later on. So therefore, all these things show that the hydrogen is the best fuel. I hope you have understood that why fuel cells have to be only hydrogen oxygen based fuel cells. The device, I have told you the device is only two component system, one anode and cathode, which is both are solids, one electrolyte. Then what is the problem? So simply a device. Fuel cell is the simplest device consisting of two electrodes and one electrolyte. From component point of view, no other device can be as simple as this. No device. Even if you take a battery, there has to be many more components. But in the fuel cell, the components are only two electrodes and one electrolyte. The essential problem appears to be the multiphasic boundaries one may have to be at the interfaces. That is the only problem. Whenever you have an interface, okay, that is a problem. This is applicable to any situation. You take two human beings, there will be a problem because two people are facing an interface. Now here the problem is more because it is an electrode and electrolyte interface. It is not two human beings, okay, not two solid objects. So therefore, the electrode, electrolyte, gas, all the known states of matter have to be simultaneously considered. This is the problem that is existing. So therefore, the device, as a device, it is very simple, but as a device, the process is not simple. So now, what do you mean by this is the question. When I have to transport an ion, I have 1 minute. Hello, சொல்லுங்கம்மா. சரி, நான் பார்க்குறேம்மா. சரி, நான் நாளைக்கு வந்து பார்க்குறேம்மா. So, so that is why I have put some philosophical statements here, but we will not worry about it. With the promise abound, but can the most common element in the universe really provide the fuel necessary to power our ground transportation system and possible energy needs? Okay, forget about this profound statement. What it means is, can hydrogen be our energy conversion parameter? Okay, now when I take this fuel cell, the components I have shown it here very simply. An anode, I hope you are able to see. A cathode, you are able to see. There is an membrane electrode assembly. The cathode and the anode is the electrodes where the catalyst is put in a kind of a membrane. We will see later on why membrane is required. So anode is the fuel electrode, electronic conductor, and catalyst. All of them are consisting of this. This is the multi-component system here. The cathode is air electrode, electronic conductor, and catalyst because it has to reduce the oxygen. Electrolyte is oxygen ion conductor, electron inhibitor. Okay, if it is a solid electrolyte. If it is a liquid electrolyte, it can be a proton conductor. Okay, so therefore, essentially, I hope you are able to see all the components. I have shown it very clearly here. So when it is a conducting, I have to put some conducting medium. That is why the carbon black is put, on which the platinum is put. We will see later on why platinum and all those things. Quickly looking at it, this is a transparency or projection given by Hariprasad. I will show it to you what I have prepared, but anyway, he has given it for some obvious reasons, so I thought I will project it to you. In 1801, I hope now you are able to see what is these two centuries. 1801, Humphrey Davy demonstrated the principle of water, what becomes fuel cell. Okay, 1839, I will show you the battery that Grove used. Okay, so you will be surprised that it is same thing. William Grove invents the gas battery for the first fuel cell. 1889, Langer and Moon developed the Grove's invention and named it the fuel cell. So nearly 100 years has taken to name this device. 1950, from that another 50 years has gone. General Electric Company invents the proton exchange membrane fuel cell. Okay, then the Francis Bacon demonstrated the 5 kilowatt alkaline fuel cell. This was immediately put 59, 60. It was put in the NASA's first use the fuel cell in space missions. Then the oil crisis in 1972-73 prompts the development of alternate energy technologies, including the phosphoric acid fuel cell (PAFC). 1980, U.S. Navy uses fuel cells in the submarines. 1990, large stationary fuel cells are developed. Molten component fuel cells are developed as standalone power generators. We will see all these things, how they went about later on. 207, fuel cell begins to be sold commercially as a product in the then in 2008, it has been used as a backup power. Honda begins leasing this Clarity fuel cell electric vehicle. Okay, 2009, residential fuel cells, microwave chips, everything became commercially possible. So thousands of portable fuel cells, battery chargers have come. Okay, so therefore this is the sum and substance of the development. Quickly looking at it, William Grove, 1839, put the two platinum strips surrounded by closed tubes containing hydrogen and oxygen in dilute sulfuric acid, produce water and electricity, but very inconsistent. I will tell you, I hope you are able to see, this is the actual device William Grove used. The picture is shown here. So that is why it is the uh, inconsistent, and that is why it is not just a minute, I will power my computer. So 1839, Ludwig von devised the term fuel cell. 1902 is the first use of the electrolyte sodium hydroxide. 52 is the Bacon's use on the alkaline medium fuel cell, and then the application in 1960s. So we will not go into all of them. Now we will go back. So now, what is the situation now? A simple chemical reaction between hydrogen and oxygen generates energy, which can be used to power a car producing only water, not exhaust fumes. The first car driven by a child born today could be powered by hydrogen and pollution free. This was the statement of the most famous person of this world, George W. Bush, in his Union address in 2003. We will not worry about it. So now, a simple fuel cell, not only simple science. Okay, that is the thing. What is happening here is, I hope you are able to see, electrochemically, what is you are putting hydrogen, producing two protons and two electrons. Now you are putting oxygen and producing water. That is all. The two reactions I have shown here. So in all the fuel cell reactions, we are going to look at these two reactions and how I will be able to maximize these two reactions. That is all. Second thing that I have to understand is, I hope you are able to see here very clearly, that the ions are transported within the system, electrons are transported away from the system. Okay, these two things we have to keep in our mind. That is why I said we are now worried about either the electrons or the ions. It is a competition. Chemists know how to manipulate the electrons. Chemists know how to manipulate the ions. So which one he wants to manipulate and which one will give him maximum efficiency? That is the question that we have to ask. That is the question we are going to ask in the fuel cells. So therefore, the simple migration of the ions is what is happening inside this fuel cell. So polymer electrolyte membrane fuel cell, phosphoric acid fuel cells, and protons are moving. This I have shown it to you before, so I will not repeat it again. You can see if PEM fuel cells and phosphoric fuel cells, the ions that are migrating is the protons. In alkaline fuel cell, for alkaline and molten carbonate and solid oxide fuel cells, negative ions travel through the electrolyte to anode, where they combine with hydrogen to generate water and electrons. Whereas here, the photons from the anode is migrating to the cathode. The signs of movement of positive or negative ions in the medium is the crux of the science here. I hope you are understanding. How will I be able to transport these ions in a unidirectional manner, either from the anode to the cathode if it is a proton, or if it is an anion, or carbon ion, or oxide ion, or hydroxyl ion from the cathode to the anode. So this is the science. The science is how will I be able to, because the ion movement alone is controlling this. Electron movement is faster here. So therefore, that is what is. The cell reaction is so simple. When I take hydrogen oxygen fuel cell, the cell reaction is so simple. It should not affect the long-term operation of the cell. As long as I have the hydrogen, it will be going on. There is no question of any disruption. The cell reaction should provide at least 1 volt or higher. I have already talked about it. Why this 1 volt is sanctity? Because the moment you are going to use the chemicals, the maximum, because we know very well the oxidation potential, reduction potentials, they are all in the ranges of 1 volt. That is all what is possible. So single species, single volt. We will keep that way for the moment. It is not true, but we will keep it. So therefore, if I were to make a fuel cell, it should be capable of at least producing 1 volt or higher. It should not produce 0.5 volt. So one can generate many cell reactions satisfying some of these conditions. Hydrogen oxygen reaction produces water and it causes minimal changes in the cell, because if it is an electrolytic medium, water is going to only change the concentration. The two reactions involved are clean and single process. I hope you are able to see it is a single process here, it is a single process here. Whereas when we take other ions, it is going to have multiple processes. Clean, I have already talked about it, clean in whatever sense you want. CO2 and other emissions are not there. Flexible, modular, many other things. Electricity generated with nuclear and PV and wind. If time permits, we will compare this new power generation from nuclear, photovoltaics, wind, and also electricity generated from fuel cell. But today we are not going to talk about it. If you want electricity, you can produce electricity by various means, including fuel cells. Storage problem in mobile applications is one issue which we are going to address later on. Okay, how will I store hydrogen is a question. Now, why fuel cells is the question. It can be because the energy conversion can be a standalone power generation or mobile power generation. For both it is adaptable. Fuel to heat to mechanical to electricity, multiple steps, efficiency is less. Fuel cell chemical to electricity, high efficiency. Fossil fuel dependence on CO2, whereas here it need not be. It can be, it need not be. Hydrocarbon reforming electrolysis, clean electron. I hope you are able to see. I have shown it here. Wow, I am getting this 1.8 volts. Okay, 2H plus 2 electron plus 2 of oxygen giving rise to water. The ideal potential is delta H by 2F. It is 1.48 volt per cell at standard temperature and conditions. Efficiency is the ideal potential versus the potential that we are getting in the cell. That is the efficiency. If I can get 1.2 or 1.5, 1.4, then it is nearly 100% efficient. This 1.4 volt is the thermonuclear voltage. Okay, it is not the electrolysis potential. I hope you understand. When I am electrolyzing water, The decomposition potential of water is 1.23, but the net energy that is required is not only the hydrogen oxygen but also the heat, therefore 1.48. We will see all these things little bit carefully later on. Okay, now let us try to answer some questions. Development of fuel cells has been slow because of, as seen by the world. Okay, we will see as seen by us later on. One, it is a higher cost compared to any other energy conversion process. Second, materials problem. Okay, we have to put noble metals and keep the noble metals in the noble state. Okay, it is very difficult to keep a noble human being always noble. I hope you understand. Therefore, noble metals also cannot be kept noble all the way times. Okay, I hope you understand this. I don't want to tell more than this. Then there are certain obvious operational inadequacies. Okay, operational inadequacies means electrolyte concentration or the potential, many other things. We will not as we know, the interface resistance, many things. So what is going to happen in the 21st century? During the 21st century, as need for electricity increases, I'm sure many of you would have already felt the electricity need for the increased electricity. The power shortage in our country has caused enormous discomfort to the human beings already. So primary fuel sources were still so abundant and not and to be exploited, but it is not going to be possible henceforth. Therefore, currently with a desire to decrease dependence on fossil fuels, emissions of the things, and also to get a sustainable solution, the fuel cells are of interest. Fuel cells with renewable energy sources. Why renewable? We have already talked about it, so we will not worry about it. It has to be sustained, and also we have to get the high efficiency. Whereas when you go in the thermal route, it cannot be efficient. All that we are going to talk about, okay, is a current versus potential. Electrochemistry means only two parameters, current versus potential. Very rarely we will talk about current versus time or potential versus time. Otherwise, many of the variations we are going to talk about current potential curves. Now what we are worried about is, I hope you are able to see the bracket that is shown, the two lines that are shown here. Okay, the dotted lines that are vertical lines are shown. So we want to operate in this region. We cannot operate in this region, or we cannot operate in this region, because if I go in this region, the potential is dropping very steadily. Here also the potential is dropping very steadily. This is the only region where the potential remains more or less, I will not say constant, but more or less steady. We are going to talk about it. This is called the current voltage curve, the polarization curve, the so-called polarization curve. We'll come to it why it is called polarization curve and all those things. Okay, because we must know, we think polarization means something more different for us, whereas here it is different. So it is the polarizing the electrode. So therefore the reaction that is taking place here, it is kinetically controlled. Here it is mass transport control. Here it is only the resistance of the cell that is controlling. We'll come to it all these things as we go along. We have 30 lectures with us, so we'll see all of them in a great detail. Okay, so we have already talked about the various types of fuel cells, low temperature versus high temperature fuel cells. We have also talked about electrolyte based alkaline polymer electrolyte, direct methanol, phosphoric acid, molten carbonate, solid oxide, or even in terms of the proton conducting or hydroxyl conducting, whatever it is, whatever way we are going to do. So now I'm going to tell you one of them. Okay, the alkaline fuel cell. Why I have taken alkaline fuel cell as the first fuel cell, even though we are worried about the polymer alkaline membrane fuel cell, we are looking at certain parameters. I hope you are able to see in this projection very clearly that what we are trying to achieve is, we saw in our polarization curve, I can get only of the order of 0.6 to 0.7 to 0.8 volts. So therefore that is what is the operate voltage that is possible. So at a fuel cell operating at 0.7 volt, I must get a current density of 1 ampere per square centimeter. That is exactly what we want. And as I said, I am worried about the anode reaction and the cathode reaction. I have shown here all the two reactions. Anode reaction in the alkaline fuel cell is very clear. That is H2 plus 2OH minus hydroxyl ions are transported, so it gives rise to water plus 2 electrons. Whereas when you go to the cathode reaction, it can be oxygen reduction, or the species HO2 minus that is formed can also give rise to hydroxyl ions. So therefore, this is a combination of the two cathode reactions. So we have to now discriminate here, or we have to make one of them not possible and only one of them is possible. We'll come to later on. So what is the typical anode? Platinum on carbon, or raney nickel platinum on carbon is the anode. Okay. So now it was developed in fancy back in 1930s. It was output in Apollo missions. Temperature is 200 to 230. Nickel anode or nickel oxide cathode. Acidic fuel cells have been used, but alkaline is faster oxygen reduction kinetics. Fuel cells were developed to provide electricity, cool the ship, and provide potable water. Okay. So now what is the limitations? It requires platinum, therefore it means a lot of rupees. Please note, I have not used the dollar symbol. I am only talking in Indian language. Liquid filled container, therefore it is a corrosive nature. So therefore the fuel cell will not last long. Now what are other problems? Compressed hydrogen and oxygen has to be kept. Potassium hydroxide electrolyte, that is another problem. You see, even with all the things, the efficiency is 70%. It is nowhere near the Carnot limitation. Okay. Now that operating temperature is around 200 degrees. You can go from 300 watt to 5 kilowatt output. That type of cells are possible. Advantage is low cost of the electrolyte solution. Potassium hydroxide is cheap. We'll come to it. Why potassium hydroxide 30 to 35? Why if it is sodium hydroxide, what should it be, and all those things later on. Okay, it is it's some kind of a ionic conduction in the electrolyte. We will come to it later on. Okay, so non-noble catalysts withstand basic conditions. Oxygen kinetics faster in alkaline solution. Okay, that is one of the reasons why alkaline fuel cells have been put into the space mission. So I hope you are able to see pictorially I have shown here. These are all taken from literature. Nothing is ours. So you can see that you are putting the hydrogen here and then getting water at the anode. Okay, here you are putting the oxygen. The hydroxyl ions are transported, and it is the electrons are going in the external circuit. Hydroxyl ions are going in the internal circuit. So now, to complete the alkaline fuel cell, at least today, I have already told you the anode has to be platinum on carbon, or raney nickel platinum on carbon. Cathode has to be platinum on carbon. Okay, the problem areas and possible solutions. We are only giving possible solutions. The two reactions we have already shown it. Therefore, I am not going to talk about it. The hydrogen at the anode, the hydrogen is getting oxidized. At the cathode, oxygen is getting reduced in two forms. The maximum current density also I have talked about it. We will come to later on why we are talking about current density and not current. Okay, we'll see later on. Okay, why current density? We have to only talk about the potential drop and the current density. We will see later on. So the catalyst platinum expensive, raney nickel wettability, chemical composition, varieties of alloys are used to reduce oxygen. Silver and cobalt can be replacing platinum. Okay, these are all the problem areas. Some of the solutions I have given here. Okay, that is already found. We are going to see other solutions that can be found in the future. We can only use pure gases. CO3 build up in the electrolyte and clogs the pores. So we cannot allow any carbon dioxide in this. Okay, so therefore that is the biggest problem. For sponges can be inserted to absorb CO2. We can only remedy this situation. Circulating electrolyte can slow build up of the carbonate. Okay, you can circulate the electrolyte and then see to it that the carbonate is not built up. But anyway, carbonate is not so therefore the alkaline fuel cell appears to be the one of the best fuel cells that is possible, and that is why it is used in the space mission. I will take only one more slide. Is the polymer electrolyte membrane fuel cell, PEMFC. which is the threatening to be the fuel cell of for our transport applications. So in this projection, I have tried to put all the information that are required in one slide. One, the current density that we are talking about, it has to be 1 ampere per square centimeter. Okay, current density. The reaction at the anode, the reaction at the cathode is written here. Okay, the transporting species is H plus. The temperature range is 85 to 105 degrees. So now, used by the NASA and Gemini mission, employed polystyrene sulfonate polymer. Okay, we will come to it. This is what is called the Nafion. I hope you are able to see the Nafion. We have to specifically spend one full presentation on the why Nafion, why not other membranes. We will come to Nafion. Nafion, developed by DuPont in 1960, currently used in most of the PEMS fuel cells. Polytetrafluoroethylene, PTFE, backbone. Okay, I hope you are able to see the backbone. Polytetrafluoroethylene with a perfluorinated side chain. I hope you are able to say perfluorinated side chain terminated with a sulfonic acid group. Terminated by a sulfonic acid group. More stable, higher conductivity. We will come to it all. What do you mean by higher conductivity and all that later on. Okay. The Dow Chemical Company also developed as a polymer similar to Nafion, shorter chain, side chain, only one ether oxygen. Okay, no longer available at the moment. It is not commercially available, even though Dow as a alternate membrane. Advantages: non-volatile membrane, CO2 rejecting system. Electrolyte few material problems. Problem is oxygen reduction is very slow. Then second problem is hydration of the membrane is difficult. I keep the membrane in a hydrated condition. So therefore the solution will be humidify the gases or impregnate the Nafion with some titanium dioxide or titanium dioxide or silicon oxide, which is capable of getting hydrated. Okay. Hydration of membrane dissociates the proton of acid group. So this proton of the acid group is dissociated. Solvated protons are mobile in polymer and provide conductivity. So this is the sum and substance of the PMFC. So we have seen already an alkaline fuel cell. We have seen the polymer electrolyte membrane fuel cell. We have to see what is the situation with the direct methanol fuel cell, and then we'll go to the phosphoric acid fuel cell, molten carbon fuel cell, and solid oxide fuel cell. After having seen all these fuel cells, then we'll go how will I, because each cell is going to give me 0.8, 0.2, nearly 1 volt, but what we want is few hundreds of volts. Therefore, we have to now look at the stacks. When I go to the stacks, what is going to happen? Then how will I make the fuel, and how will I be, what are the vocabulary that I am going to use in these presentations? These are all vocabulary, it is not definitions. Please understand this. When I use electrochemical reaction, I am not defining the actual electrochemical reaction, the net chemical reaction that is taking place in the fuel cell, which is responsible for the generation of the potential. So that is why the vocabulary is different here. So I have to define all the vocabulary. Then we will, in the course of this, we are going to look what is the thermodynamic principles of the fuel cells, what is the kinetics of the electro process, what are the fuel cell components, and what are the available choices, what are the choices that are not yet explored. This is what is going to be the main point of our discussion. Why they have not been exploited, why they have to be exploited. Then fuel cell support systems and considerations will come later on. There is because a DC voltage is being produced and AC voltage has to be, therefore there has to be some inverter and other things. So therefore there must be a support system. Now we are going to talk about finally current research issues and where do we stand. So this is all the presentations that we are going to do in the course of this online course. Now I will leave it to you to ask any questions that you want. Any questions you can ask.